All right, we're continuing LeChatelier's principle today. This is kind of part two. Yesterday, what we took a look at was, first of all, what is a stress? What does that look like at equilibrium? What happens when a stress is applied? And we talked about the fact that if a stress is applied in your life, you have to shift things. You have to readjust your time allotments for different activities and things like that if something happens in your life, right? Well, same thing for a natural system. If an increase in concentration happens for some reason, or a decrease in concentration, if the change in pressure, okay, if there's a change in pressure, if there's a change in temperature, all these are stresses. And we're going to talk about today, we're going to talk about what happens when pressure and temperature are changed. So yesterday were these notes here on the change in concentration, and today we're going to focus on these guys right here. If pressure is increased, okay, so we're talking about pressure now. If pressure is increased, or the volume is decreased, which really means the same thing, right? If you decrease the volume, there's not as much space for all those reactants and all the molecules that are involved, not as much space for them to move around, so they end up kind of bumping into the container with a little bit more pressure, okay? There's not as much space for them to kind of chill out. So volume is decreased, same effect. This will translate into larger concentrations for all of the gases involved. Now, there's a second part to that, because if pressure increases, usually there's a shift in equilibrium. Sometimes there's no shift, sometimes nothing happens, but most of the time something happens. So I'm going to expand on this one a little bit. So I don't know if you left room in your notes when you copied this out or not. My notes down here. Okay, so let's say we have 2 moles of A, and this is in the gaseous state. Now, A is just some random, reactant, okay? And we have 3 moles of B, and this is also in the gaseous state. So we got a little G there for gas. We have a reversible reaction, and that's going to produce 3 moles of C, and this is also in the gaseous state. So this is all gas. We have a reversible reaction, and we are at equilibrium, okay? This is at equilibrium. If the pressure increases, so if we have an increase in pressure, as we just wrote down, all of the concentrations of the gases will increase, okay? So that's great. A new equilibrium will be established, and sometimes, like I say, there's a new K value, but you don't see a shift sometimes. But most of the times you do, and I'll tell you where the shift happens. Now think about this. So say we've got 2 moles, so here's a mole, there's a mole of A, and we've got 3 moles of B, and we've got 3 moles of C, okay? So this is a bit of a representation here. And if the pressure increases, so let's say we have a volume, like this, and I have a volume like this, and that gets decreased, okay? So now we have less of a volume. See that? The volume is decreased, therefore the pressure is increased, and this is now the only available space. What it's going to do is all of those moles are going to be higher in concentration, and the side with the most moles of gas are going to be forced to react more. Okay, so you got to think about this. We have 1, 2, 3, 4, 5 moles of gas represented on the reactant side, and we have 1, 2, 3 over here. So what's going to happen is these are going to bump into each other a little bit more. And these, yes, this is going to react as well, but there's so many more moles on the left side that it's going to cause more product to be made, and there's going to be a slight shift in the equilibrium. Okay? So increased pressure, all right, the side with the most moles reacts and it shifts the equilibrium the other way. So all we said was that the moles increase, and I can't write over here for some reason. There we go. So let's add to this. When pressure increases, when pressure is increased, the side with the most moles of gas reacts more So, once again, when the pressure is increased, the side with the most moles of gas reacts more, thus causing a shift in equilibrium the other way. So, another way to put that is it favors the side with the fewer moles. So if you have a few moles on the right side, you increase pressure, there's more production on that side. Okay? So that's a little expansion here of the pressure. Right? So if there's bits of solid over here, you just consider the moles of gas. So let's change this. So this one right here, if we were to change this, and this is solid. And that's solid over here, then we have 2 moles of gas on this side, and we have 3 moles of gas on this side. We do not even consider the solid here. So if this was the case, increase in pressure here would shift the equilibrium that way. Does that make sense? Okay, it shifts towards the side with the fewer moles of gas. So we should make sure we remind ourselves of that, of gas. Alright, so let's talk about temperature then. Okay, temperature. If temperature is increased, okay, now generally, if temperature is increased, generally, the reaction rate increases, right? Because there's collision theory, there's more colliding, more successful collisions. We know that. But we also have to consider something a little bit deeper. We have to consider a deeper level of what's happening here in the system. Okay? Consider the enthalpy change. Now, who knows what enthalpy means? Anybody know what enthalpy means? Okay, enthalpy is sort of another word for heat. Okay, heat content. It's H is what it represents, and the enthalpy change is the delta H, or the change in energy of the system, for the most part, change in heat energy of the system. So, if the enthalpy change is if the reaction is endothermic. Okay, so do you know what endothermic means versus exothermic? Yes, endothermic absorbs heat, exothermic releases heat. Think of endoskeleton. Okay, and we have endoskeletons. Okay, if you think about biology, think about science. Because our skeletons are inside. Exoskeletons, like crabs, that sort of thing, right? They're outside. The protective is outside. See that? So we are inside skeletons, endo. So inside, within. So take the energy within. Exo is release of energy. So when you burn propane, that's highly exothermic because it releases heat. Okay. Okay. Other reactions. If you mix something together and there's a chemical reaction and it feels cold, the beaker feels cold, that means it's sucking the heat in to make the reaction happen. That's an endothermic reaction. Or a phase change, right? Can be endothermic, can require heat. Ice to water, that requires heat. Okay? Not a chemical reaction, but it's a phase change, but that's endothermic, requiring heat. Okay? And technically, if water freezes, okay, it's giving off heat. Okay? So, anyways, that's a different discussion. But exothermic, okay, so if the reaction is exothermic, the addition of heat translates into addition of product. Alright, shifting the equilibrium toward the reactant side. Okay, so let's just talk about that for a second here then. If we have A plus B, and let's just take a look at one side at a time. A plus B is C, and this has a delta H, okay, that is negative. So you guys don't have a lot of experience, I don't think at this point. A lot of you said you weren't really too sure about exothermic, endothermic. Exothermic is giving off heat. That means there is a negative change in delta H. Okay, so if heat is being given off, the change in enthalpy is negative, and so that's like this: plus energy. Okay, energy is a product when delta H is negative. If we have C going to A plus B, the delta H for this same reaction in the reverse direction would be positive. That makes sense? So that means we have energy over here. Energy plus C. Okay? So our reversible reaction then is A plus B is in equilibrium with C, and we have energy over here because it's being given off in the forward direction. So if we add heat, then it's like we're increasing one of the products. Okay? And if we increase one of the products, what has to happen? There's a shift towards which way? Yeah, shift towards reactants. So if this is the setup, if we have the forward reaction is exothermic, we have energy on the product side, an addition of heat will shift it back this way. A removal of heat would be like the opposite effect, right? A removal of heat, if we decrease the temperature, then we have a shift this way. Now in the video you took a look at, they taught you about kind of the scale view, right? Here's balanced. If you add something, the scale goes down like this, and then you have to, shift things this way to get back to balance, right? You may like that. That's not the way I view it. I'm kind of a visual learner myself. And can I tell you how I picture this? You guys might like this, you might not, okay? But this is just a little bit of how I do things. And I can't write on that side of the screen. All right, so if this is equilibrium, I picture it like a pool of water, or like a dish of water, or something like that. And here's the middle. We've got reactants, and we've got products over here. If I increase a product, it's like I have a big volume of water that's pushed up here. I know it's not always realistic, but where is that water going to flow to establish a new equilibrium? It's going to flow this way, right? It's going to level out. So it's going to be like this, and it's going to level out until we have a new normal. The old equilibrium levels were down here. Now the new equilibrium, it shifts this way, first of all, right? And establishes a new equilibrium. If you have that same sort of idea, okay, here's equilibrium, and you take away some product, well, that's like a hole. It's like a space to be filled, and what's that water going to do? What's that pool going to do? It's going to rush in to fill the hole, right? And so you have a new equilibrium, but it's going to shift this way. So I don't know, however you want to look at that. It's kind of an opposite way of looking at it if you look at the scale, or if you look at sort of this way. But if there's a stress and you increase product, it's going to shift equilibrium, so there's more production of the reactant, and opposite, vice versa. Okay, so that helps me. And again, for temperature, just think about energy as either a product or a reactant. Well, it'll tell you that, so like over here, right, the forward reaction is exothermic. That means that energy is on the right side. If the forward reaction was endothermic, energy is on the left side here with the reactants. Okay? So there will be some delta H here for one of the reactions, the forward reaction or the reverse reaction. Then you'll know. Okay, so that's a little supplement here. We talked about pressure and temperature as well. So changes in equilibrium, changes in pressure has to do with gases only. And change in temperature, you got to take a look at where the energy is, where the energy would be in the reversible reaction. And then treat it like an increase in concentration of energy if heat is added or heat is subtracted. Okay, so that's a little bit more on LeChatelier's principle. As we finish off here, what does it say? A reaction is endothermic. A temperature increase is an addition of a reactant. So that's the way you look at it. Okay, and that just kind of follows what we said. If the forward reaction is endothermic, a temperature increase is like an addition of a reactant, and it will shift equilibrium to the right. Okay, so you can take a moment to Just add that to your notes if you don't already have it.